Hey guys, here in this lectures, we're gonna be more example for Lenz's law, and then we're gonna cover the second topic regarding for the AD current. So the first example here, we have a current and go to the wire here and the square located beside it. And the question asks for the, if we increase the current or the time or the current to the wire will be increasing, is there is any induced current in the square loop, and if there is any other direction. So basically using the right hand rules, we can find out the magnetic field will be pointing to the base. And this is the magnetic field. And since the current will be increased, that basically means the magnetic field inside the loop will be increased. Okay? With the increased magnetic field, or to call it about flux increase, flux will be increased. When flux increase, we're gonna Lenz's law reduce the B induced. And B induced will be just to resist that increase, to cancel that increase by producing the induced magnetic field point out of the base. So here's the out of the base. So from we have the induced magnetic field, by default, we have induced current. What the direction for the induced current? Again, we're gonna use the right hand rules. We can find the magnetic or the induced current will be pointing clockwise, counterclockwise, sorry. Okay, so let's move for second example. In this example here, we have two loops, and the current goes to outer loop, and they ask there is and that current is gonna be increased. What the directions of the induced current in inner loop? We're gonna talk about the perspective from the Lenz's law. What happened for that? So the first one, when I have the current, we're gonna use the right hand rule to find the magnetic field producing from the outer loop. So the right hand rules, we're gonna be find the magnetic field will be point out or point in that direction up, and that magnetic field will be cross the inner loop and the same direction. So we have that one here pointed up, and here we call it the magnetic field comes from the outer loop or from the outer current. Now, based on the magnetic field cross the inner loop right now, talking about magnetic field cross inner loop, when they increase the magnetic field or increase the current, increase the magnetic field, Lenz's law, we have increased flux. So we have flux increase. The same thing, flux will be increased. That's the answer for this case. And since the increase, so the Lenz's law, the loop will be resist that change. We're going to produce the magnetic field in opposite directions. And that directions here, pointed down. Okay, here it's going to be pointed down. Here is the B induced down, and induced current in that case, right hand rules, we will find it that directions will be, here is the clockwise directions. Okay, so even if the current is not go to the inner loop, but still produce the induced current in inner loop. Let's move for another example here. In that case, we have a magnetic field, and that magnetic field just in that circle that's shown up in that figures. And we have the outer square, which basically electrical circuit has include two light bulbs. And if the magnetic field, we increase the magnetic field in that loop, the question is do the light bulb will be light, and what the direction of induced current. Again, we're going to start it to in the second part when we stated the magnetic field will be increased. The magnetic field will be increased, so we have flux. Flux will be increased. So the loop will be resist that increasing. So going to be produce their own induced magnetic field. Be induced will be out. Now current, induced current. Induced current. So we're going to use the right hand rules. We find the current will be in this directions. Counterclockwise. Regarding for the light bulb, this one's, do the light bulb will be light or not? Yes. It will be light since we have the induced current. The last example here, we have the loop and wires are being pulled up into the regions where there is magnetic field. We take that loop or the square, bolted up in the regions. And what happened here, what the direction of the induced current. So when we increase or when we pull up the square inside the magnetic field, the flux will be increased. We're going to be resist that increasing by reducing the magnetic field pointed out of the page. Point out of the page, both in or into the page, and based on that, we can find the induced magnetic field will be in that directions. So magnetic field will be clockwise. Let's see for another example here, or sorry, another topic here, what we call AD currents. The AD currents here, if just you imagine we have the piece of the metals here, and we have the magnetic rod in the top of it, and we just drop down the magnetic rod down to the metals here. So when you reduce it in that case, the flux will be increased. So assume any loop, or here's the imaginary loops, and base it in the magnetic field, that the loop will be changed. So we have the loop, and that the loop would be when we point it close to the magnetic field, close to the metals, it will be reduce or increasing that case, and we're gonna reduce or produce the induced magnetic field. And that increased magnetic field will be point up to resist that increasing for the magnetic field comes from the rod. And once the induced magnetic field generated, in that case, the induced current will be generated as well. And the induced current generated here, it will be counterclockwise. That the current here, what we call it the AD current. And since this one is the mini loop, imaginary loop, so we have imagined all the loops here generated the imaginary loops, and it has many induced or the AD currents in it. Okay. So another perspective here, if you look at the magnetic or the induced magnetic field pointed up, so we can imagine this one as another magnetic rod here, and the north part will be point up. So in that case, we can imagine this, the induced magnetic field, as another magnetic rod, and just try to resist the change in the flux. Okay? That's another magnetic field rod. So this is idea, it has many applications. One of the application here, what we call making metal detectors. So basically what that idea here, we have the transmitter coils where there is a current, and we have the receiver coils and the receiver, and we have induced the magnetic current here and magnetic field, and that transmitter has a magnetic field. And if the part of the metal comes in the middle, transmission and the receivers, we're going to produce the induced current. That induced current will be decrease the transmitted or the induced current here. So since that one, so the induced current in the eddy part here, oh, something changed for the receiver coil. Since they're reducing the current inside the receiver coils, we know that something happens, maybe piece of metals located between those two. This is the one applications for emitter detector.